Hello students, how are you doing? You are watching video series for grade 10 advanced physics, and in this video we will be discussing all the questions from the textbook from chapter 2 lesson 1 properties and detection of sound. So we will start with first question. I am Amir. A warm welcome to Mass Academy. Question 1 is about the intensity of sound. How much more intense is a sound that registers 80 decibel than one of 40 decibel sound? So we have two sounds here with a sound pressure level L1 that is equal to 80 decibel, and another sound that is 40 decibel. L2, the sound pressure level of the second sound is 40 decibel, the loudness, right? So the intensity of the first sound that we will write I1. I1 is the intensity of the first sound. It has a loudness 80 decibel, and I2 is the intensity of the second sound. So we know that here L1 has more decibel, right? More decibel, more loudness, so it will be more intense. So the L1 sound, the 80 decibel sound will be more intense compared to the 40 decibel sound because its loudness is less. But how much greater? That's what we have to know. So what is the equation to compare the intensity? I1 divided by I2, that is equal to I1 divided by I2. The intensity of this sound divided by intensity of the second sound, that is equal to 10 to the power L1 minus L2 divided by 10. 10 to the power L1 minus L2 divided by 10. So 10 to the power, what is the value of L1? What is the sound pressure level or loudness of the first sound? 80 decibel, right? So 80 minus, what is the second sound? 40, right? 80 minus 40 divided by 10. So what is 80 minus 40 divided by 10? 80 minus 40 is 40. 40 divided by 10, that is equal to 4. So 10 to the power 4. I1 is I1 divided by I2, that is equal to I1 here, right? I1 divided by I2, that is equal to 10 to the power 4, means the intensity of the first sound I1 is 10 to the power 4 times the intensity of I2. What's the meaning of 10 to the power 4? 10 to the power 4 is 10,000. So 10,000 times greater. I1 is 10,000 times greater. Why 10,000 times greater? Because it has more sound pressure level or more loudness. Okay, so this is the solution. And if you want to make it simple, like this, for example, how many times greater? So we will do like this, 80 minus 40 divided by 10. How much? 80 minus 40 is 40. 40 divided by 10 is equal to 4. So how much more intense? This 4 you have to write here, okay? 10 to the power 4 more intense. So the intensity of the first sound is 10 to the power 4 times the intensity of the second sound, which means, so you got the answer, right? You already got the answer for that question. I'm just giving some explanation. So if there is a 10 decibel increase in the loudness of the sound, if there is 10 decibel increase in the loudness of the sound, then intensity will increase by 10 times. Intensity will increase by 10 times. For example, there is a sound, it has 40 decibel, a 40 decibel sound and a 50 decibel sound. Which one will be more intense? Of course, 50 decibel will be more intense. How much more intense? 10 times more intense, because Yeah, 50 minus 40, that is equal to 10. 10 divided by 10, 1. So 10 times intense. Then another sound, okay, there is another sound, a 30 decibel sound and a 60 decibel sound. Which one will be more intense? 60 decibel sound will be more intense. Why? Because it has high value of loudness. How much more intense? 60 minus 30 divided by 10. 60 minus 30 is equal to 30. 30 by 10 is 3. So 10 to the power 3 times more intense. The 60 decibel sound is 10 to the power 3 times more intense than 30 decibel sound. 10 to the power 3 is equal to 1000, right? So the 60 decibel sound is 1000 times intense than this 30 decibel sound. When there is a 10 decibel increase, the intensity will increase by 10 times. When there is 20 decibel difference, then intensity will increase by 100 times, 10 to the power 2 times. When there is 30 decibel difference, then there will be a difference in intensity 10 to the power 3, that is 1000. Question number 2 is also related to the sound pressure level, that is the loudness of sound. How many times greater is sound pressure level of a typical rock concert? It has a loudness 110 decibel than a normal conversation. It has a loudness or sound pressure level 50 decibel. So what is the difference in sound pressure level? The difference in sound pressure level, that is equal to 110 decibel minus 50 decibel, that is equal to 60 decibel. So what will be the difference in intensity? The difference in intensity will be equal to, so you can see here there is a difference of 60 decibel in sound pressure level, right? There is a difference of 60 decibel in sound pressure level. If there is a difference of 10, then if there is a difference of 10, the difference in intensity will be 10 to the power 1. If there is a difference of 20 decibel in sound pressure level, if there is a difference of 20 decibel in loudness, then intensity will differ by 10 to the power 2. If there is a 20, right? Yeah, 10 to the power 2, correct. If there is a difference of 30 decibel, then intensity will be greater by 10 to the power 3. So here there is a difference of 60 decibel, so intensity will differ by 10 to the power 6. So here this sound, which is sound? The typical rock concert, it has a decibel of 110 decibel. It has a sound pressure level 110 decibel, and the normal conversation, it has a sound pressure level 50 decibel. So this sound, the typical rock concert sound, will be 10 to the power 6, means 1 million times greater in intensity, 1 million times greater in intensity than the normal conversation. Question number 3 is from Doppler effect of sound. A guitar player sounds 523 Hz while traveling in a car at a speed of 24.6 meters per second. If the car coming towards you, what frequency would you hear? Assume the temperature is 20 degrees Celsius. So what is the frequency that detected in Doppler effect? So we have the equation Fd, that is equal to the frequency of the source multiplied speed of sound minus speed of the detector divided by speed of sound minus speed of the source. So this is the equation of Doppler effect. So first, what is Doppler effect? That we have discussed in that previous video. What is Doppler effect? For example, you are standing here and a car is coming towards you. A car is moving like this. So when the car is moving towards you, you will hear an increase in pitch of the sound produced by the car. So when the car is moving towards you, you will hear an increase in pitch, and when the car is moving away from you, you will hear a decrease in pitch. When the car is moving towards you, increase in pitch. Pitch means frequency. The frequency, you will hear the increasing frequency of the sound. And when the car is moving away from you, you will hear a decreasing frequency of the sound. Means when the source of the sound is coming towards you, the frequency will increase. And when the source of the sound is moving away from you, this frequency will decrease. That is the Doppler effect. And in this equation of Doppler effect, what is FD? FD is the detected frequency. Detected frequency. Detected frequency means pitch. The detected frequency is called pitch. Detected frequency means at what frequency the listener is listening that sound. At what frequency the detector is hearing that sound, that is represented by FD. Then what is Fs? Fs is the frequency of the source. Frequency of the sound produced by the source. So I will write frequency of the source. And what is V? V is the speed of sound for this question or this lesson. V is speed of sound, and Vd is the speed or velocity of detector. Detector, correct? Okay. Then what is Vs? You know that, right? S represents the source, so speed of source. Okay. So here a guitar player sounds 523 Hz. So Fs we know. So what are the things we have? Fs, Fd, F. So we will okay. Fs, Fd, F, and V, Vd, Vs, many things, right? Can you see this? If I write in at the bottom. Okay, so what we will do here, I will write. Okay, then F as frequency of source, frequency of detector, frequency of source, frequency of detector. Then V speed of sound, Vd speed of detector, Vs speed of the source. Okay, so here what is the frequency of the source? Means how much frequency how much is the frequency of the sound produced by the source. Here the guitar is producing the sound at what frequency? 523 Hz. 523 Hz, that is the frequency. And what is the frequency of the detector? Means at what frequency the listener is listening that sound. Will it be the same? It will not be same, because the source is moving. The person using the guitar, he is inside the car and the car is moving towards you. So you will not hear a frequency that is 523. You will hear the sound which has a frequency greater than 523. Why? Because the source of the sound is moving towards you. That is what you need to calculate. What is V? V is speed of sound, not given in the question. So here it is given, assume the temperature is 20 degrees Celsius. At 20 degrees Celsius means at room temperature. The speed of sound in the air. So there is air, right? Between the car and the detector there is air. The sound is traveling through the air. And if the temperature is 20 degrees Celsius, that is room temperature, then the speed of sound is 343 meter per second. Then what is the speed of the detector? The detector is not moving. You are not moving. You are just standing there. So your speed is 0 and the source is moving, right? Source is moving at what speed? The source, actually the guitar and the player, the person is inside the car and the car is moving with a speed of 24.6. So the person's speed or the speed of the source, speed of the guitar is 24.6 meter per second. So here you can see the source is moving towards the detector. If the source is moving towards the detector, we take the velocity positive. So this is the sign convention in Doppler effect. The direction from source to the detector is positive. The direction from source to the detector is positive. Then what is the opposite direction? If the detector is moving towards the source, then negative. So this is the sign convention, okay? SD, from S to D, you can remember SD, S to D, right? S to D, source to detector is positive. Then so detector to source is negative, okay? For example, if the source moving away, then what is the direction? Source is moving away, right? Then it will be negative, okay? So S to D is positive and the opposite direction, for example, this direction will be negative, okay? So we will solve this question. So to solve this question, we need some space. I will erase this part. So we need to calculate FD. FD is equal to Fs. How much is the frequency of the source? 523, and speed of sound is 343, minus speed of the detector is 0, divided by speed of sound is 343, minus speed of the source is how much? 24.6. 24.6. Take the calculator, on the calculator. Yeah. 523 multiplied 343 over 343 minus 24.6. Our answer must be greater than 523, right? Okay. So the answer is 563 hertz. 563 hertz. So this is how you have to solve, or you need to solve the problems, numerical problems from Doppler effect using this equation. In this question, the car was moving towards the detector, right? So we got an increase in the frequency of the sound that the listener, that the detector is hearing. And if the car is moving away, right? So we said like the direction from the source, this is the source, this is the detector, that is positive, right? The direction from source to the detector, towards the detector, is positive. So if the car is moving in the opposite direction, the car is moving away from the detector, so what happens? This direction will be negative, right? So this direction will be negative direction. So speed will be negative in that case. So what happens to the frequency if the car is moving away? What was the original frequency? The original frequency was, the guitar is playing at a frequency of, the guitar is making a sound at a frequency of 523 hertz. And if the car is moving away, the frequency the detector hearing will be less than 523, right? That is the Doppler effect. If the source is moving away from the detector, the frequency that he is hearing will be less than the actual frequency of the sound that is produced. So here the actual frequency of the sound produced is 523, and if the car is moving away from the detector, the frequency the person is hearing must be less than 523. So that we will check in that calculation using that equation. So if the car is moving away from the detector, the speed will be negative. What will be negative? the speed is negative. So what we will write, instead of writing 24.6, we will write negative 24.6. So here negative and negative, right? So the negative and negative will become positive. So what will be the frequency of the sound? So we will check 500, okay, 523 multiplied 343 divided by 343 plus 24.6, that is equal to how much? 488 only, 488 hertz. So do you understand from this question, when the car was moving towards you, the frequency was greater, right? So I don't remember what was the previous answer. I hope that is 568 hertz. Okay, so when the car is moving towards you, the frequency you are hearing is increasing, and when the car is moving away from you, the frequency you are hearing is actually less than the actual frequency produced by that guitar. That is the Doppler effect. Question number 4, from the Doppler effect, you are in an automobile traveling towards a pole mounted warning siren. If the siren's frequency is 365 hertz, what frequency do you hear? Use 343 meter per second for speed of sound. So here there is a pole and here there is a siren. So this is the siren, and you are here, you are in a car. Okay, so you are in the car, here the car is here, the car is moving towards the siren, the car is moving towards the siren, right? The car is moving towards the siren. So here you are the detector, right? You are the detector. So here detector, you can see detector is moving towards the source, right? Detector is moving towards the source. So this is the situation, and we will write what is given in the question. We have frequency of the source and frequency of the detector, and speed of sound we have, speed of sound. Then we need a speed of the detector, speed of the source. These are the 5 things, right? Yes. So what do we need to calculate? We need to calculate the detector frequency. Means what frequency you are hearing that siren. So what is the actual frequency of the siren? That is given in the question, 635 hertz, right? Where did we get 635 from the question? That is given here. So what is the speed of sound? The speed of sound, you can take 343 meter per second. That is also given in the question. Take the speed of sound is 343, right? That is given in the question. And what is the speed of the detector? The detector is in the car, right? At what speed the car is moving? That is given in the diagram, okay? In the diagram it is given as 25 meter per second. So in the figure it is given the car is moving at a speed of 25.0 meter per second. So that I forgot to write before. So speed of the detector is 25.0 meter per second. And what is the speed of the source? Source is on a pole, right? It's mounted on a pole, so the pole is not moving. Speed of source is 0 this time. So we need to solve the question. So I need some space here. So I will erase this. Before I erase, I will tell this one, the important thing here. You can see the car, means you are inside the car and you are hearing that sound, so you are the detector. So this time the detector is moving towards the source, right? Because siren is producing the sound, so siren is the source, and the detector is moving towards the source. So I said the direction from source to detector, not from left to right, okay? Not from left to right or up and down. No, from source to detector is positive. Source to detector is positive. Now the detector is moving towards the source, right? The detector is moving towards the source, so speed will be negative. Don't think like that this is also to the right side, then I took positive. This also to the right side, then I took negative. No, not like that. Source not right or not left. That is not the sign convention here. Here what is the sign convention? Here the sign convention is this, the direction from source to the detector is positive, detector to source negative. So here the speed will be negative. Now I will erase this. Why am I erasing this? Because I want to write here. So here, what? Detected frequency, we have the equation of Doppler effect, that is equal to frequency multiplied speed minus speed of the detector divided by speed of sound minus speed of the source. That is equal to frequency, how much? 343 minus Vd, speed of the detector, minus 25, right? Minus 25.0 divided by 343 minus speed of the source not moving, speed is 0. So what? Take the calculator. 365 multiplied 343 minus will be plus 25 over 343, that equals 392 hertz. 392 hertz. So here you can see the actual frequency of the siren is 365 and you are hearing a frequency that is 392, means you are hearing a greater frequency, right, of a sound. Its frequency is greater than the sound produced by the siren. Why? Because you are moving towards the source. That is Doppler effect. If the source is moving towards you or you are moving towards the source, you will hear an increase in frequency in the sound. That is the Doppler effect. Now I am not writing the question on the board. I will read from the textbook and you will see the question at the bottom. Reach it, right? Okay, so you are in an automobile traveling at 55 miles per hour, that is equal to 24.6 meter per second. A second automobile is traveling towards you at the same speed. Its horn is sounding at 475 hertz. What is the frequency do you hear? Use 343 meter per second as the speed of sound. So what? So you are in a car, you are in this car, you are here, you are traveling at a speed of how much? 24.6 meter per second, 24.6 meter per second. And another car, a second car, so the second car is making horn, so this is the one producing the sound. So we will call that source. That is also traveling with the same speed, 24.6 meter per second towards you. So you are hearing that horn sound, which means you are the detector. You are the detector, right? Detector. Okay, so you are the detector. You are the detector and you are moving with a speed of 24 meter per second, so 24.6 meter per second towards the source, and the source car which is producing that sound, right, that is moving towards you with the same speed, and that car is producing a sound of 475 hertz. What's the frequency of the sound? 475 hertz, and the speed of sound is given, that is 343 meter per second is the speed of sound. So in Doppler effect we have frequency of the source, frequency of the detector. Frequency of the source is given in the question, that is 475 meter per second, and frequency of the detector, that is what you need to calculate. Then we have speed of sound, speed of detector, speed of the source. Speed of sound is given 343, that will be always positive, and speed of the detector is given, that is 24.6 meter per second. Speed of source also 24.6 meter per second. So here you can see The speed of the source, what is the direction? It is moving towards the detector, right? The source is moving towards the detector. I said the direction from source to detector is positive, right? So this is positive because the source is moving towards the detector. So this is positive, and detector is moving towards the source. It will be negative. When detector is moving towards the source, that is speed will be negative, and we need to calculate the detected frequency using the equation fd, that is equal to fs multiplied speed of sound minus speed of detector over speed of sound minus speed of the source. Fs is how much? 475, and you know that here the answer will be greater than 475. The reason is here the detector is moving towards the source and source is also moving towards the detector. The frequency will be greater. What is the speed of sound? 343 minus speed of the detector is minus 24.6 divided by 343 minus 24.6 equals 475 multiplied 343 minus will be positive. Why this is minus? Because that is the speed of the detector. Here the detector, that is you, are inside the car and the car is moving towards the source. That is why the direction from detector to the source, not from left to right, okay, not towards right side positive, no, that is different thing, that is coordinate system, different thing. In Doppler effect here, the direction from source to detector is positive and detector to source is negative. That is why your speed is negative, the speed of the detector is negative, and minus will be plus, right? So plus 24.6 divided by 343 475 multiplied 343 plus 24.6 divided by 343 minus 24.6 equals, so I am getting 548 hertz. It's much greater, right? The actual frequency was 475. Now the frequency is 548. 548 hertz is the frequency of the sound that you are hearing. The frequency of that horn produced by that car was 475 hertz. At what frequency you are hearing the horn? You are hearing the horn at a frequency of 548 hertz. That is Doppler effect. Now we are discussing our question number 5. So here there are two submarines, and this submarine is producing a sound. Its frequency is 3.5 megahertz, that is 3.5 times 10 to the power 6 hertz, because mega means 10 to the power 6, right? Million. That is 10 to the power 6. Then this submarine is moving with a speed of 9.2 meter per second towards the second submarine, and you are in this submarine, you are there, and you are detecting, means you are hearing this sound produced by this one. And the submarine you are in, the second submarine, that is not moving, and the speed of sound in water, that is not 343 is speed of sound in the air. In water the speed of sound will be much greater compared to this one, and in water, in that depth, the speed of sound is 1482 meter per second. That is given in the question, and you can read the question from the bottom of the video. So here, how to write what is given in the question. So first we will write the frequency of the source, frequency that you are detecting, frequency of the source is 3.5 megahertz. So I will write 3.5 times 10 to the power 6 hertz, and frequency of the detector, that we will calculate the detected frequency, and the speed of sound, speed of detector, speed of the source, right? So what is the speed of sound? 1482. That will be always positive. Don't worry about the sign. Speed of the detector, detector is not moving, so its speed is 0. And speed of the source 9.2, it is moving towards the detector. So S2D, right? S2D, source to detector will be positive. Okay, so what is the equation? Fd, that is equal to speed of, source frequency, right? Fs into speed of sound minus speed of the detector divided by speed of sound minus speed of the source equals the actual frequency, that is 3.5 times 10 to the power 6 multiplied frequency, speed of sound 1482 minus 0, because the submarine you are in is not moving, so you are at rest, divided by 1482 minus 9.1482, right? 82 minus 9.2 equals 3.5 times 10 to the power 6 times 1482 divided by 1482 minus 9.2. So I'm getting 3.52 times 10 to the power 6 hertz. So here you can see before the frequency was 3.50 and now the frequency is 3.52, right? Means there is an increase in frequency. The increase in frequency is due to the source is moving towards the detector. Source is moving towards the detector, right? Question number 6. So here there is a trumpet, right? Okay. That is producing a sound. Its frequency is 262 hertz, and you are the detector, you are away from the trumpet and you are here, you are hearing that sound and you are hearing at a frequency of 277 hertz. You are not moving, you are at rest. You know that you are not moving, right? You are at rest. But you are hearing a frequency that is actually greater than the frequency of the sound the trumpet produces. So you know that the trumpet, or we know that the trumpet must be moving towards the detector, right? So the trumpet must be moving, this is the source, right? It must be moving towards you with a speed Vs, but that is not given. That is what you need to calculate in this question. So how to calculate that? We will write what is given here. So frequency of the source, frequency of the detector. So here frequency of the source is given 262 hertz. Frequency of the detector also given 277 hertz. What else is given? Speed of sound 343 meter per second. Speed of the detector, you are not moving, right? 0. Source is moving. That is what we need to calculate, that speed. Okay. So speed must be, you will get positive, right? Positive value. So what's the equation? Equation is detected frequency, that is equal to frequency of the source into speed of sound minus speed of the detector. Speed of the sound minus speed of the detector. Detector is not moving. Divided by speed of the sound minus speed of the source. Speed of the source. So this is our equation. We will rewrite this equation because we need to calculate speed of the source, right? So I will take this to this side, V minus Vs. That is equal to how much? Frequency of the source multiplied, this V minus 0 will be V, divided by Fd will come here. So we will calculate like this. What is the frequency of the source? Source frequency is 262 multiplied. Speed of the sound is 343 divided by frequency of the detector. At what frequency are you hearing that sound? 277 equals how much? So we are getting 262 multiplied 343 over 277 equals 324. 324, that is V minus Vs. V minus Vs is equal to 324. We need Vs, right? So I will take Vs to the other side of the equation. So I will write here, okay? I will continue here. Vs is equal to V minus 324, right? So what is the value of this V? This is 343 minus 324. That equals 343 minus 324. That equals 19 meter per second. 19 meter per second. That is the speed of the source, means speed of the trumpet. Maybe the person who is carrying the trumpet is moving with a speed of 19 meter per second towards you. So without doing these rewriting and all, I can find the answer from here itself by using the shift solve in the calculator. So that we will do here. So how to use shift solve in the calculator instead of rewriting all these things? So FD, what is the value of FD? 277, right? So I will write 277 here. That is equal to Fs, how much? 262 multiplied, what is this V? The value of V is 343 divided by, this V is 343 minus alpha x. So I will use that 277 alpha solve 262 multiplied 343 divided by 343 minus alpha x, shift solve equal, then wait for some time. Yes, 19 meter per second. 19 meter per second. So you can use a shift solve in the calculator to get the answer directly without rewriting the equation, and you can save time and you can avoid mistakes while rewriting the equation by using that option in the calculator. The next question, wave characteristics. What physical characteristics of sound wave should be changed to alter the pitch and the loudness? The pitch is related to the frequency of the sound. So to change the pitch of the sound, we need to change the frequency of the sound, and the loudness is related to the amplitude of the sound, and to change the loudness of the sound, we need to change the amplitude of the sound. The next question. The eardrum moves back and forth in response to the pressure variation of a sound wave. Sketch a graph of the displacement of the eardrum versus time for 2 cycles of 1 kilohertz tone and a 2 kilohertz tone. So 1 kilohertz and 2 kilohertz frequencies, right? Frequency of first one, F1, 1 kilohertz KHZ, and frequency of the second one, that is 2 kilohertz. So how to draw? So the first one, we need to draw 2 cycles, right? 1, 2. 2 cycles. So what will be the time taken? The time taken to complete. So this is the time axis, and this is the displacement axis. So 1 kilohertz. So what will be the time taken here? It must be 1 millisecond, right? One number of waves completed in 1 second. So if one wave is completed in 1 millisecond, that is 10 to the power negative 3 second, then in 1 second 1000 waves will be completed, right? 1000 waves will be completed. So this is the 10 to the power means 3 seconds, or I will write like this 1 millisecond. So or we will write like this. Here we will write time in millisecond, So this is 1, this is 2, this is 0.5, this is 1.5. So we can draw like that. Then for the second one, so we have to draw the 2 cycles, 1, 2. In this, it is completing, this wave is complete, its frequency is 2 kilohertz. 2 kilo means 2000, right? The frequency is 2000 hertz. 2000 hertz means this wave is completing 2000 waves in 1 second. 2 kilohertz means 2000 hertz, which means 2000 waves in 1 second. So 2000 waves in 1 second means 2 waves in 1 millisecond. So here this is the time axis. So time we will label in millisecond. So in 1 millisecond it is completing one wave, 1 millisecond, okay, 1. So if that is 1, then this will be 0.5, right? This will be 0.25, this point, and this point will be 0.75. And this is the time axis, this is the displacement axis. So this is how we need to draw the wave graph of displacement against time for a wave. It has a frequency 1 kilohertz. 1 kilohertz frequency means the wave is completing 1000 cycles, 1000 waves in 1 second. And we have to draw 2 cycles, right? So if it to complete 1000 waves in 1 second, which means what is the time taken to complete one wave? The time taken to complete one wave is 1 divided by 1000, right? That is called 1 millisecond. 1 millisecond. So the time taken to complete one wave is 1 millisecond. Here I labeled time in millisecond. So here it takes 1 second to complete one wave, 2 seconds to complete 2 milliseconds, okay, 2 milliseconds to complete 2 waves. So this is 0.5 millisecond, this is 1.5 millisecond, like that. The next question, in the 19th century, people put ears to a railroad track to get early warning of an approaching train. Why did this work? So here you know that railway track is made of steel, right? Made of steel or made of iron. Railway track is made of steel. So in solids, in metals, the sound travel at a greater speed. Sound travel about 5000 meter per second. The speed of sound in metals around or nearly equal to 5000 meter per second. And what is the speed of sound in the air? That is only 343 meter per second, which means the sound travel much faster in the metal. So in the railway track, you can see the railway tracks are made of steel or made of metal. So in like in old days, people keep their ear on the railway track to sense that there is a sound. It shows the train is approaching or train is coming. As the sound travel much faster, they can know earlier than they actually hear the sound through the air. So that is the reason. And question number 11, this I have actually explained in my previous video of the lesson about how the bat is using the Doppler effect to locate its prey in the echolocation process. A bat emits short pulses, high frequency sound and detect the echoes. Short pulses means it emits pulses of sound with a small duration. Okay, small short pulses the bat emit with a high frequency. So it will be emitting large number of pulses in a very short time. In what way would the echo from large and small insect compare if they were the same distance from the bat? So for example, the bat using the Doppler effect to detect its prey, bat is emitting the ultrasound waves. It will hit on the prey and it will come back. How the bat know whether the prey is very small in size or very large in size? That the bat can know from the intensity of the reflected ultrasound. The bat is emitting an ultrasound wave, emitting pulses, right? A number of pulses in a short time with an intensity, right? So when it hits the small prey, only small number of waves, small number of pulses will be reflected back, because the size of the prey is very small, right? So all the pulses will go here and there. It will go, means it will pass the prey, and very small number of pulses will be reflected back. So if the intensity if the intensity of the reflected sound is less compared to the emitted sound, the bat can know the prey is in small size, the object is in small size. If the object is large size, then it will reflect most of the pulse the bat emitted, most of the pulses bat emitted will be reflected. So when the bat receive that reflected sound, it will receive large number of pulses, right? Means greater intensity, right? Greater intensity. From that, the bat can understand the object reflecting this sound has a greater size, a large size. Okay, so bat estimate the size of the object or size of the prey by comparing the intensity of the reflected ultrasound. If the intensity of the reflected ultrasound is much less, which means the size of the prey is very small, and if the intensity of the ultrasound reflected is greater, which means the size of the object which is reflecting the ultrasound with the reflecting that sound is large. In what way would the echo from an insect flying towards the bat differ from that of an insect flying away from the bat? So when the bat use this echolocation process, how do the bat know whether the prey is moving away from the bat or it is moving towards that? By difference in frequency, the shift in frequency, the change in frequency of the reflected sound. For example, the bat is emitting the ultrasound waves, so it hits the prey, right? It hits the object, it hits the prey, and the sound will be reflected. The bat will receive the reflected sound and it will compare the frequency of the reflected sound with the frequency of the emitted sound. If the frequency of the reflected sound is greater than the frequency of the emitted sound, which means the prey is moving towards the bat. If the frequency of the reflected sound is less compared to the frequency of the emitted sound, which means the prey is moving away from the bat. If the frequency of the reflected sound is same as the frequency of the emitted sound, which means the prey is not moving, it is stationary there, it is standing there or sitting there. Okay, the next question: can a police using a radar detector at the side of the road determine the speed of the car at the instant the car passes the police? Explain. So I am a policeman standing beside the road like this, and here a car is traveling and I have a radar here. So this is my radar. I use my radar like this. So this is the road. Okay, you cannot see the road because my table is there lower. So here there is a road and this car is moving on the road and the police standing here with a radar here. See, the car is moving like this. Can using this radar measure the speed of the car? Can this radar identify whether the car is overspeeded or not? See, the car is moving like this, moving along this. It cannot because you can see here car is moving along this direction, right? So what happens? The radio waves from the radar will hit the car and will be reflected. The car is not moving to this side or not moving to that side. The car is moving along this side, right? So there will be no change in the frequency of the reflected radio waves. So if you are a police, where do you have to stand? I am a police, so I have to stand here and keep the radar like this. The car is coming, the radio waves from the radar will hit the car, will be reflected, car is moving. If it is moving over speed, there will be a greater difference in the frequency of the reflected radio waves. This is the end of this class, and in this class we have discussed all the questions given in the textbook in chapter 2 lesson 1, properties and detection of sound. Thank you students for watching this video. Good luck.